Every morning I used to do 1 hour mathematics since 25 years. You know, I'm not a mathematician, I do it for fun, but I like proofs. And when I make a proof, somehow my brain clicks in a mode that's good for science.
Jeantet Roska, who holds a medical degree from the Semmelweis Medical School from Budapest in his home country, Hungary, lives not just for mathematics, but also for neurobiology and genetics, specialisations he subsequently moved to in the USA. Passionately interested in neuroscience, it's in Basel where he now continues his research into a specific field, namely ophthalmology. We perceive the outside world through vision, a physiological mechanism which has fascinated scientists, philosophers and doctors for centuries.
20% of human brain is about vision. We are visual animals. So when we lose vision, we lose our social environment, we lose communication, and unfortunately, the number of blind patients is going up exponentially.
Understanding the eye's mechanisms and finding the underlying reasons for the diseases affecting it and its functions is what led Jeantet Roska and his team to take a closer interest in the human retina and to discover its secrets. The human retina is so specific, so unique. While it's possible to understand how vision works by investigating animal vision, the pathologies affecting the human eye are very specific.
5 years ago or 6 years ago, we never dreamt about working with human retinas, but technology comes by and then we ride with new technology. One of them is that we can take post-mortem a retina and we can record from these retinas. And the other one is that nowadays, from a skin biopsy, we can build retinas from skin cells, from patients. Indeed, we can build hundreds of retinas from a single patient. This new technology allows us to study diseased retinas, multiple diseased retinas in a dish. So we can look how a disease develops and we can design strategies for repair in a dish.
Organoids, cellular structures developed in the lab which reproduce the microanatomy of organs such as the retina. They may represent both healthy and diseased organs and allow Jeantet Roska's team to identify the cells where specific pathologies originated.
Here we see a cross-section of an organoid. Basically, we make very thin sections of the organoids for analysis. So this is one way we can analyze them, and we can stain them with antibodies. Here on the outside, that's the photoreceptors. In fact, the photoreceptors among the retinal cell types are one of the cell types that is affected by disease a lot. So many inherited retinal degenerations lead to loss of photoreceptors, and when we lose our photoreceptors, we are blind.
Blindness, macular degeneration, glaucoma, or simply short-sightedness, the diseases affecting the eye are numerous and usually recognisable. But it's what causes them which is of interest to eye specialists.
Over the last decade, we have seen tremendous technical advances that allow better and better examinations of the eye. As an example, we can see the individual layers of the retina of a patient in real time. But while diagnostics have advanced so much, therapies to cure eye diseases have not kept the same pace.
Hendrik Scholl and Jeantet Roska met at the Basel Eye Clinic. They quickly realised they should share their knowledge and jointly focus their ambitions.
I think it's a luck that two of us working in the eye with the same goals happen to be in Basel. But then I think that once you have these two components, I think it's evident that this is a way to go. To get new therapies, we have to put together research and clinical science.
Jeantet Roska and Hendrik Scholl together founded the Institute of Molecular and Clinical Ophthalmology in Basel. This was a challenge made possible by three partners who opted for putting ophthalmology centre stage.
It was not the time yet to have breakthrough chances, and now it converges. The molecular genetics, the possibilities to treat single cells or influence single cells, and modern technology, computer-based approaches. So I think it's also an opportunity now that technologies are around that can be integrated to have promising impact for patients.
The main objective was to improve the understanding of the function of the eye, of eye diseases, and to treat impaired vision and to help patients with blindness or impaired vision to have a better sight.
While eye diseases may attract less attention than deadly conditions, such as cancer or heart disease, the medical and societal burden is rising. Myopia, for example, affects a large number of people all over the world, especially in Asia. Given this background, we must intensify our research and bring the best scientists and clinicians together to learn more about the underlying causes of disease and develop new breakthrough therapies that can make a real difference to patients.
We have two programs in IOB. One is to make photoreceptors that lost their light sensitivity gain, to bring them to clinical trials. And we have another program which we would like to repair using gene therapy. We would like to do gene therapy in Stargardt disease. It's a juvenile macular degeneration. In case of the light sensitization, we call it optogenetic therapy. This is about to restore vision in blind patients. In a case of gene therapy in Stargardt disease, we would like to slow down the degeneration.
In parallel to these clinical research projects to discover new treatments for eye disease, Jeantet Roska and his team are also interested in the circuits linking cells in the retina with the nervous system.
From a neuroscience perspective, it's a very interesting challenge because the retina is a major input into the central nervous system, and it's one where a lot of processing occurs before you send the information back. So there's both the nice thing that there's an input that's known, light, an output that's known, the actual potentials down the optic nerve, and processing in the middle, and it's very relevant for our livelihoods.
People say the eye is the mirror of the soul, a window on our brain. So mysterious, so fascinating.
It's still a big mystery of what the retina tells to the brain and how the brain uses this information to create a percept and to conclude about the visual scene. And here, unlike our understanding of retina, we are at the very beginning of the road. And I believe that many brain diseases can also be diagnosed at the level of the retina. We can understand, we can treat, and we can monitor ongoing therapies.